In computer, everything is data structure. So from now on, let's look at the data structure for process. When you create a process, creating a process is allocating a memory, but more importantly, creating a process is creating a data structure for the process. Then what is the data structure for process? There is a common term that represents the process, which is called process control block. Um, Process control block. It is a common term to represent the process. So what does the process structure should contain? So let's say the struct process. In some in some operating system, it is called struct threads. So the struct process contains an information about, well, of course, the most important information is going to be process ID. And also, the process priority is also the important information the process structure should have. Anything else? And of course, the for the process to run, it requires a file and it requires memory. So you should contain the memory related information. So it should contain the um, text segment, location of the text segment, location of the heap segment, location of the text segment. Also, it should contain the information about the files it is using. So it's file information. So this is, of course, and then in some process, it may contain the register information, which we call is called context. So process control block is an abstract data structure that represents a process, and it contains important information like process ID, process priority, virtual memory information, file information, register information. So these are sort of the data structures that represent a process. Okay. And then once you have this process data structure, operating system, in the operating system, there is lots of processes. Okay. So there is process one, there is process two, and there is process three, and many, many else. Process maybe 1/10 of the 24. So, operating system maintains all the process data structure as a linked list. Long before operating system maintains processes as an array of processes. For example, in early days, System 5 Release 6, operating system maintains an array of 64 processes. So there can be as many as 64 processes in the system in all these 1970s. But uh, these days, a server may contain thousands of processes. So these days, operating system maintains a set of processes in the system as an array, probably the double linked list. Okay, so this is process list. Also, well, there is another important data structure. We saw that in CPU, we maintains uh, a set processes that are waiting to be executed. For example, here there is CPU, and there is a queue of processes waiting to be executed. Okay, which we have called it as a ready queue. Okay. However, in reality, ready queue is also implemented as a list of processes. So ready list, there is another list. It's called the ready list. So ready list of ready processes or processes in the ready state. For example, P1 and P2 is not in the ready state. P3 or blah, blah, blah. Yeah, sorry. Okay. So there are four important data structures we need to remember. Is that okay? There is a process control block, which we usually call as a struct process or struct thread, and it contains process ID. I mean, if you design your process data structure by yourself, then it's all yours. You know, you should be able to add any amount of fields or attributes you think it's right for the process data structure. But normally the struct process should contain process ID and priority of the struct process and memory-related information that is being used by the process and file information that is being used by the process and then register information for, which is also called context. So there is important data structure. First one is process control block, and second one is process list, and third one is read list. I said there's four. Okay. The fourth one is process context. Okay, these are four important data structures you need to remember. Okay, let's look at the code actually. Um, um, our text is based upon the x86 operating system, and we are dealing with the Pintos operating system. So there are two different differences. Sorry about that. Um, so if you go to the PowerPoint slide and let's open it up, and um, so this is the thread structure in Pintos. So the struct thread. As you see, there is a thread ID, it's a process ID, and this is state of the process. Um, the process can be in one of the three states: blocked, ready, or running. Of course, the operating system may be able to define a few other processes state. And interestingly, Pinterest defines a name for the process. This is for debugging purpose. And this is the memory information, the pointer to the stack it is using. This is priority and blah, blah, blah. And this is thread structure for Pinterest. And this is process structure for x86 kernel. So same as before, it contains process ID, which is of course mandatory for every individual process structure. And then there is a process state field, and then there is somehow uh, this process structure doesn't seem to have priority field, does it? Okay, so in XV6, the process does not have a priority. That's very interesting characteristic. And also it contains information about the files it is using, and it contains data structure called struct context. This is a set of registers the process is using. So in XV6, the process structure explicitly maintains the set of register values in its process structure, whereas in Pintos operating system, the process structure does not. And then let's look at the code. Okay, the first one is thread structure. So let's find, this is Pintos code, and let me just expand the window. I'm using an Emacs. It should be thread.h. Okay, so from here you see the struct thread. This is data structure for struct thread. It contains thread ID and state of the thread or process is the same. And then yeah, so that is it. And then in Pintos there is a list. Pintos maintains a list of processes in the system, and the name of the data structure is all list. So here, if you see the thread.c file, it defines the all in the list data structure. So every time when operating system creates a new process, it inserts the thread structure to this list. And once the data structure, process structure is destroyed, it is removed from the structure. And another important list is ready list. Ready list. Okay. So this is simply ready queue. It maintains the set of processes that are ready to run for the CPU. So So we covered three basic data structures. Thread structure, a list which maintains all sets of processes in the system, and ready list which defines the ready queue. That's that's pretty much end of the process data structure presentation. Thank you. From now on, I'm going to explain the APIs for manipulating process. There are three major APIs for manipulating process. First one is fork. The second one is exact. The third one is wait. And then I'm going to explain why the Unix operating system separates the fork and exec. The, the first function I'm going to explain is fork. It is used to create a child process. First, the child process is allocated memory space from the parent process, and that memory address space is initialized with the contents from the parents. The child process has own registers and it has own program counter. Once the child process is created, it becomes independent. So it becomes a just normal process and it is scheduled altogether with the other process that has been running. The last important thing is that for the parent, fork returns process ID of the child process, and for child process, fork returns 0. Probably the fork function is the most weird form of function you'd ever combine. You see a function p1.c. It calls a fork. Let us look at the details of the program. It prints a hello world function to the screen. And then it calls fork. And then there is just normal code, C code. Then this code, this p1.c creates a child process. Let's say the process A is parent process. So before there is only one process, process A. After process A calls fork, then the operating system creates identical copy of the same process under a different process ID. So on the right hand side, the process ID of the process A was 12370. Now, the newly created process, the child process, it looks identical, right? This lady and this lady looks precisely identical, except that they have different process ID. The parent process is returned the child process ID when fork is called. And the child process is returned 0 when the fork is called. When a fork is called, it is something like that operating system creates the same copy of the process which is identical to the parent process, and then it starts to execute the fork. A fork starts from the fork function of a child process. This is just before fork is called. The result of the fork is going to be 0. The result of fork in the parent process will be returned the process ID of the child process, which is 14,871. Based upon the process ID of the fork, the parent process and child process can distinguish the code they want to execute. If the process ID is greater than 0, then it means that this process is parent process. It prints the parent. If the process ID is 0, then the current process is child process that has been created as a result of fork. It prints child. The parent process, after printing the parent, it calls the wait. Wait system calls make the caller to block until the child process finishes. There is no temporal dependency between the child process and the parent process. Let's say there is parent process, and in the course of executing its own function, it calls fork. Then at this point, the child process is created. So now there is parent process and then child process. So after calling fork, parent process proceeds and child process proceeds. We do not know whether the parent process is executed first or the child process executed first. You might want to enforce the order of execution between the two, and that is the role of wait. If parent process calls wait, then the wait system call in the parent process won't return till the child has run and exited. This is the way they explicitly enforce the order between the two. Now let's look at this code. In the course of executing the child process, it prints to the screen that I am child, and then it prints out the process ID. We have added a wait function at the parent process code. The wait function does not have any parameters. In this view graph, we show how the relationship of execution between the parent process and the child process proceeds. At the beginning, there is only one process, and it calls fork. And then after creating a child process, as a result of calling fork, a new process called process B is created. But because there's only one CPU, process A continues to execute, and then it reaches the function wait. Because wait system call waits for the child process to finish, it is still blocked here, and then CPU switches its context to the child process. And then process B starts to execute, and then at the end, it reaches the exit statement. The exit statement, after exit statement, the child process finishes execution and it disappears because it has finished this execution. And then, after then, the parent process of the wait system call resumes, and then it continues to execute the rest of the code. We can guarantee that child is executed first, and then the parent executes. I am going to explain the way how Unix operating system running a new program. Fork system call creates a process, but fork system call creates the identical copy of the parent. What if the parent process wants to run a different program? For example, you want to launch an editor, or in the command line you type ls-l to list up the files in your directory. For that purpose, operating system needs to load a new binary image and then initialize a new stack and initialize a new heap for the new program. This is basically the operating system has to do to run a new program. That is the role of exec. Exec takes two parameters. One is the name of the binary file it wants to execute, and the second one is the array of arguments that needs to be passed to the exec function. You are seeing a piece of code that calls exec. Before calling exec, this program creates an address array of three strings: echo, hello, and null strings. And then exec is called. Exec has two parameters. First one is the name of the binary file it wants to execute. And second one is the array of strings that needs to be passed as an argument to the binary file it wants to execute. This is actual usage of exec system calls. Exec system call has many variants, and here the variants of the exec system call that is being used here is exec VP. First, this process calls fork, and this is the code executed by child process. And this is the code executed by parent process. Let us look at the code executed by parent process first, because it looks simpler. It contains 3 lines. At the very beginning of the code, it waits for the child to finish. So the parent process is blocked until the child finishes. Then what the child process do? It first prints out the string, hello, I am a child, and then it sets up a certain array of strings. The first parameter is wc, and the second parameter is p3.c, and then it creates argument string. And then in the function of exec vp, it passes the first parameter of my args as a first parameter to execvp. Here, the first parameter is wc. So apparently, this program wants to execute a command wc, which is word count. Word count counts the number of words in a file. And then it passes a name of the file it wants to use as an input to a word count command. This screen explains what happens when exec is called. When the exec is called, the operating system replaces the existing contents of a memory with the new memory contents from the new binary file. Important thing is that exec does not return. Whatever code there remains at the rest of beyond the exec, it won't be executed. Here, there is a print statement after execvp. Exec function does not return. The printf statement, this shouldn't print out. Okay, let's get back to the slide. So when we call exec ls, for example, so there is process A, and then somehow in the system core, they call exec here. And then after exec is called, all the binary images of data stack and the text segment of process A is replaced with the new binary image for running an ls. So first, the binary image of this part is replaced with the binary image of ls function. And then the heap and stack are also initialized and reallocated. This screen shows the result of executing P3. After executing P3, it generates a hello world screen to the screen. And then the child comes executed first. After the child is printing out the hello I am child, then it calls exec and it runs wc, its word count statement. So actually the output of the word count is printed out on the screen and the child returns. And then the parent is waiting for the child to finish, and after child finishes, then parent go ahead and prints out the string to the screen. Hello, I'm a parent of blah, blah, blah. So this is the result of exec. The next question is, why are we separating fork and exec? Why don't we just use something like fork and exec? There is very, very important philosophy behind this separation, and it is the fundamental invention of Unix operating system to make the I/O redirection and pipeline pipe possible. So this is a very, very important concept. I/O redirection is something like this. If you type cat w3.c greater than you found that text, then output of cat3.c is saved to new file.txt instead of being displayed on the screen. If you use pipe, then you can use an output of a program as an input to another program. That is the pipe. In actuality, pipe is the heart of the shell programming, is the key invention of Unix shell. I/O redirection redirects the IOs for standard input and for standard output. Here you see a sample command, word count 3.c. It is supposed to print out the number of words and number of characters of the word 3.c to the screen. However, if you use a redirection symbol, then all the outputs that comes from the WC is redirected to new file.txt and it is stored. This is the simple code that does I/O redirection. It first creates a child process. And then if it's a child, then it closes the stand.out file number and instead it opens a new file and then it calls exec. Then for this whatever program that has been passed to exec's function, all the output that goes to the standard output in this statement that goes to p4.output. To understand the I/O redirection, there are a few concepts we need to understand. First one is file descriptor. File descriptor is an integer that represents a file or pipe, a directory, and a device. So I guess you are familiar with this statement. So when you open a file, it returns an integer, unsigned integer. It's greater than 0 always. Okay. And then when you read from a file, and when you write to a file, as a first argument to the function, you supply the file descriptor. Then what is the meaning of file descriptor? Every process has a table called file descriptor table. It's the table of file descriptors. So it is numbered from 0 to maximum of 256 in these days Linux version. So these are the array of file descriptors. And then what is the contents of the array? Here there are from 0 to 225 file descriptors. And then what does it contain? What is the meaning of entry of the file descriptor table? It is a pointer. It points to something. What does it point? Every file has an offset. When a program writes to a file, or when a program reads from a file, it applies the operation starting from the current offset. That is called offset. Offset is a distance from the beginning of the file. Every operation, it first has to examine the offset, the current offset, and it starts the application. Where is an offset? Where does it reside? Operating system maintains a data structure called file struct that harbors the offset. So file structure contains a variable called offset. And this data structure is created when a file is open. Offset denotes the location where the read and write operation has to be applied, and the data structure called file struct harbors the data structure called offset. Open system call creates a file structure. This file structure resides in kernel's address space. A process called open or fopen, then it first creates a file structure, then it creates a pointer, and then it sets the pointer, points to the just created offset file structure. I'm going to explain the file descriptor and the associated system calls. First one is open. When you call an open system call, it creates a new file object, and it contains an offset for a file. And then also in the file descriptor table, the open system call searches the file descriptor table from the beginning and finds the first free entry, and then sets the pointer of the file descriptor table that points to the file object. Okay, that's open system call. Closed system call is the other way around. It first removes the file's associated file descriptor entry, and then and cuts the pointer. And if none of the file descriptor actually refers to the file object, then the closed system call also deallocates the file object as well. In fork, it copies the file descriptor table from the parent to the child process. The child process has its own file descriptor table, but the file descriptor table entry actually points to the same file as the parent points to. Exec retains the file descriptor table. This is very important. When you exec, it loads new binary file, and it initialize new stack and new heap area. However, it reuses the file descriptor table inherited from the parent. So it does not reinitialize the file descriptor table. It reuse the file descriptor table. File descriptor table. This is very important. Let me explain what the IO redirection is in detail. Here, there is a file descriptor table. File descriptor 0 represents standard input, and file descriptor 1 represents standard output, and file descriptor 2 stands for standard error file. From this file descriptor table status, if you close file 0, and if you open input.txt, then let's see what happens. As a result of closing the file descriptor 0, you will cut this link and make the first entry of the file descriptor table free. When you open the file input.txt, it creates an input.txt data structure which contains an offset of the input.txt file, and then operating system says the first element of the file descriptor table points to the input.txt. So as a result of closing the file 0 and as a result of calling open input.txt, the state of the file descriptor table looks like this. In particular, you have to pay attention to this part. So normally, the file descriptor table entry 0 represent a standard.input file. But now, it points to a file called input.txt. Normally, you call this function to read input from the screen. So read, and you supply the first parameter as a standard input, and then you specify the buffer you want to save the incoming character string. Okay. However, if you set this function and if you call this redirection, then as a result of calling this function, you will read the stream from the file input.txt instead of reading the input from the standard input. This is another form of IO redirection. Here, we close the file descriptor 1 and we open output.txt. So as a result, we cut the file descriptor pointer of that points to the standard.out, and then since we open output.txt, operating system scans the file descriptor table and find a free entry and then set the pointer points to output.txt. As a result, this parameter will point to the file object that represents output.txt. So once the file descriptor is set up this way, if an application calls write 1 buff 1024, then it writes to the file descriptor 1, whatever it represents. Here, 1 points to the file output.txt. If you perform this write system call, then instead of writing the character string to the standard output, which is a screen, it prints this string to a file whatever specified by this file descriptor. In our case, this is output.txt. This is how shell implements the cat. Okay, so there is a fork. So after it creates a process, it calls an exec, and as a parameter, it supplies cat, and it passes the file it wants to print out on the screen. However, in between, it closes the file descriptor 0 and reopens the input.txt. As a result of executing these two statements, the first element of the file descriptor table points to the file called input.txt. Then, how is the cat implemented? And then it reads a file, it reads the standard input, and then it writes the contents to the standard output. So read from the standard input and writes to the standard output. That's what cat does. That's very simple. However, if the shell calls exec for executing cat statement, it closes the file descriptor 0 and relinks the file descriptor 0 to input.txt. So as a result of this IO redirection, when the cat code calls read with the file descriptor 0, it reads the contents from the input.txt instead of reading the contents from the standard input. Now I'm going to explain the concept of pipe. Pipe is a key innovation of Unix shell. Pipe is a feature that output to a standard output of one process is fed to the standard input of another process, and is implemented with this basic system called DUP and pipe system core. And it is key innovation of Unix shell. For example, there is echo hello world, and then you put a vertical bar, and then you type WC, which stands for word count. Then the output of echo hello world is fed to the word count. So this is how it works. So there are two processes. There are parent process and there are child process. And if you connect these two processes as two processes with a pipe, then the parent process writes to pipe, and then the child process read from the pipe. The first system call you need to understand is DUP. Is DUP, and it accepts a file descriptor as a parameter. Then it duplicates the file descriptor. Let's say there is a DUP and it accepts a parameter n, which stands for a file descriptor. This is file descriptor table, and there is nth index, and it points to a certain file object. If you call a DUP with parameter n and it returns the value and you save the value to m, the operating system scans the file descriptor table and then finds the first free entry and then copies the value of a file descriptor table entry to the entry n. So as a result, the file descriptor n and file descriptor m points to the same file object. The result? Let's look at the code. If you call DUP1, for example, then file descriptor 1 and file descriptor fd will point to the same file. So if you write hello to file descriptor 1, and then if you write word to file descriptor fd, then they both will go to the same file. The next system call we're going to cover is a system called pipe. If pipe is called, it creates a special file called pipe. It is called special because it contains two file descriptors. First one is for read and the second one is for the write. So file descriptor is supplied an array of two integers where the operating system stores the two file descriptor. So like this. So integer, you define the array of two integers and then you call a pipe with p. Then you create a special file with two file descriptors. So this is file descriptor table. And then if you call pipe p, then the operating system scans the file descriptor table and then finds the empty entry here and here. And then it creates a file and then it creates two offsets and then save the file, save the file descriptor table entry that points to the offset here and here. Important thing is that the first element of a two integer array stands for the read end of a file, and then the other one, which is second entry in the array of two integers, stands for the write end of a file. Let us read the code that uses pipe. So there is word count, and then we call pipe. So we create a file that has two file descriptors. At the beginning, the layout of the file descriptor table look like this. So there are three elementary file descriptor arrays which are initialized at the beginning of process creation. Standard in, standard out, and standard error. And then you call pipe. And then you create a file with two file descriptors. So P0 is standing for the read end of a file, and P1 stands for the write end of a file. We are going to execute this simple example. So echo hello world. So we are going to execute hello world, and then we supply the output of hello world to the input of the word count. After executing fork, we have just executed fork, and then new process has created. And then it copies the contents of the file descriptor table. So there are also two file descriptors that points to the read end of a file and then also write end of a file. Now let's execute the next statement. We just executed fork, and then this is child process. We close a file dex of 0, and we create DUP P0 and close P0 and P1. So first, we close P0. So we close P0 here. Okay. So this element becomes free. And then we call DUP P0. DUP P0 is this one. So we duplicate the file descriptor that has been represented by P0 table, find the empty entry that has been just freed before, and then sets the value to point to the same file descriptor that has been pointed by P0. This is read end of the pipe file. And then it closes P0 and P1. P0 and P1. It closes P0 and also it closes P1. And then it calls exec. Now, with this file descriptor table status, the WC is called. Now, let's execute the parent's code. It first closes the P0 file descriptor, and then it writes hello world to the file that is pointed by P1, which is this one. And then it closes P1. So as a result, the parent process writes hello world to the file. And then a child process reads whatever string there is from this pipe file. So this is how the pipe is implemented. What is the advantages of pipe over using the IO redirection with temporary files? For example, here we type echo hello world and type WC. In the second statement, we perform echo hello world and temporarily save it to the temporary file. And then using the IO redirection, we use just created /temp/xyz, which contains the output of echo hello world, and supply it to WC as an input file. So in both cases, word count will count the number of characters and number of words embedded in the character string hello world. When you use pipe, the pipe automatically cleans whatever temporary files there is. Whereas if you use temporary file, then you have to explicitly delete /temp/xyz. Also, in pipe, the child and parent will execute it in concurrent manner. But if you use temporary file and IO redirection, you cannot start WC until you finish echo hello world. We have explained the concept process, and we cover the basic APIs for manipulating the processes. That is fork, exec, and wait. And also, as the last parts, we have explained the reason behind the separating the fork and exec.